Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on March 3rd, 2026, just 5 days ago. It introduces a feed-forward foundation model that efficiently tracks the 3D trajectory of every single pixel in a video, shifting away from slow optimization frameworks to a much faster pairwise scene flow approach. The paper is titled Track4World, Feed-Forward World-Centric Dense 3D Tracking of All Pixels. And as we'll see later, the model shows some really impressive memory and efficiency gains, with significant implications for real-world 4D reconstruction. Okay, Figure 1 illustrates the core pipeline of the Track4World model. On the left, it takes standard monocular video frames as input. Then, in the middle, the model estimates both dense 3D points and scene flow, which essentially represents the 3D motion of every pixel between any arbitrary pair of frames. Finally, on the right, these pairwise flows are fused to reconstruct complete, world-centric 3D trajectories, meaning it successfully tracks all pixels in a global coordinate system. Alright, Figure 1 just sketched the general setup, and now Figure 2 walks through the method details step by step. On the far left, the system naturally starts with the input video frames. Moving to the second stage, the model constructs a global scene representation, relying on a 3D foundation model to extract essential geometric features, point clouds, and camera poses. The heavy lifting happens in the third block, which handles dense flow estimation. It uses a sparse to dense decoder to predict motion between arbitrary frames, and introduces a 2D to 3D correlation module that drastically cuts down computational costs by avoiding full 3D spatial searches. Finally, the far right shows how these pairwise flows are fused into continuous, world-centric 3D tracks. So the previous figure laid out the overall architecture, and now Figure 3 directly compares the correlation mechanisms. The top panel illustrates how previous methods tackled dense 3D correlation, relying on explicit K, nearest neighbor searches, and cross-attention in 3D space, which quickly becomes computationally expensive. In contrast, the bottom panel details the proposed 2D to 3D approach. By anchoring 3D updates directly to intermediate 2D image plane correlations, this new design significantly improves computational efficiency and even allows the tracking module to be boosted by abundant 2D training data. Well, after Figure 3 detailed the correlation mechanisms, Table 1 evaluates scene and optical flow estimation. The top half shows results on the in-domain Kubrick 3D dataset, split into short and long-range settings to test different temporal gaps. The bottom half then evaluates generalization on two out-of-domain datasets, Kitty and Blink Vision. Across key metrics like EPE3D or 3D endpoint error, which measures the average distance between predicted and actual 3D motion, the proposed method consistently outperforms existing models. Highlighted in darker blue, Track4World achieves superior accuracy in both 2D and 3D flow tasks, demonstrating strong robustness. Okay, Table 1 established the flow estimation accuracy, and now Table 3 evaluates 2D tracking performance across 3 different datasets. The columns break down the results for kinetics, RoboTap, and RGB stacking, which challenge the model with complex camera motion and robotic manipulation. The evaluation relies on average Jacquard, which jointly assesses geometric and occlusion accuracy alongside visible point fractions. At the bottom, the proposed model achieves state-of-the-art results, outperforming strong baselines like CoTracker 3 and LocoTrack. Alright, while Table 3 just showed the 2D tracking performance, Table 2 now presents the assessment for 3D tracking. It relies on the average percent deviation, or APD, metric to evaluate accuracy across several datasets, testing both 16 and 50 frame temporal lengths. The top half compares methods in the camera-centric coordinate system, where Track4World shows strong gains over baselines like Pomato and Zero MSF. The bottom half shifts to the world coordinate system, proving that the model consistently delivers state-of-the-art results in global tracking as well. So, while Table 2 established the tracking accuracy, Table 8 now compares computational efficiency. The columns measure time, memory, and parameter count for 16 frame sequences. In the middle, those gray rows show that STV2 and a variant missing the 2D to 3D correlation module both crash with out-of-memory errors during dense tracking. Finally, at the bottom, Track4World efficiently completes the task, requiring just 14 gigabytes of memory and 26 million parameters. To wrap up, Track4World represents a major step forward for 4D scene reconstruction. By relying on efficient pairwise scene flow, the model finally makes dense, all pixel tracking in a global coordinate system, practical and scalable for complex real-world videos. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.